So this is Thumper, our half-size mouse. We decided to make as Thumper. Let's get rid of a couple of these place-holding slides. Get to the start. Okay. Right, we are Derek Hall and Jim Chidley, and together we've been building Micromouse since 1983, with our first entry in 1984 Earls Court Computer Fair. And yes, that is a picture of me in 1984, when I was 17. So I haven't changed a bit. Today we're going to be looking at our first half-size Micromouse. Okay. Over the years, we've built a lot of mice. This is by no means an exhaustive selection of our creations. We built mice with 2 wheels, 3 wheels, 4 wheels, 6 wheels, and even one with 1 wheel, using stepper motors, DC motors, you name it. We've probably tried it. Some have been more successful than others. But we've never built a mouse that doesn't turn when it gets to a corner. Okay, this year is the 40th anniversary of the mouse in the UK. We don't count last year, it doesn't exist. We thought we might create a mouse. We thought we might start by creating Sterling Mouse. That was the first mouse to ever get to the center of the maze. Yeah, I know it was actually there. But it was really just a two-wheeled stepper mouse with an innovative mechanical sensor that probably is above our fabrication ability. That you might be able to do it with a 3D printer. It would be interesting. So we decided to go for a mouse type that we've never tried before. Dave Woodfield's 1981 entry, Thumper. Thumper does not turn the whole mouse when it gets to a corner. Instead, it turns the 4 wheels underneath, leaving the main part stationary. It was also the first, and as far as I know, the last mouse that could talk, using a Robotics SC01 speech chip as used in arcade and pinball machines at the time. Here's a video. Okay, did the video work okay for everybody? Got here. Right, Thumper's name is no accident. It could only turn all 4 wheels together using a single motor. So to correct twisting errors, it would deliberately slam into walls. And with the weight of Thumper measured in kilograms, Thumper earned its name. We wanted to build a half-size mouse to kickstart the contest in this country. We've had a maze for several years, and up until now, as far as I know, only 1 wall-following entry. The half-size contest is run on a maze with all the wall dimensions divided by 2. This means that the mouse would have to be 1/4 the size to fit in. To put that into context, the UKMARS bot would have to be smaller than a credit card. The maze can also be up to 32 by 32 cells, so considerably more complex. The photograph here is of a half-size maze in Hungary in 2015. So we have a bit of catching up to do. Also, the mouse had to be built in using parts from our junk box, as international post system seemed to have shut down for a while. Luckily, we have a very extensive junk box and a resin 3D printer. The main microcontroller is an Arduino Nano with a USB micro connector instead of the more usual USB mini. Despite the color and the connector, everything else is a standard Arduino Nano. The reason we wanted to use a USB micro connector was so we could try programming it using a magnetic USB lead that turned out to be absolutely fantastic, allowing connection of the programming lead to be very quick. If you do get one of these, make sure you get one that has data lines, as an awful lot of them seem to be power only. To reproduce the voice, we went for a DF Player Mini. This is a tiny, the size of a micro SD card slot, MP3 player that can be controlled using a standard serial port, and also includes an amplifier for the speaker. It plays from a built-in SD card slot up to 64 gigabytes, so it can say a lot. It is a four-wheel drive, four-wheel steer mouse. Each wheel has a motor with a planetary gearbox. The weight of the mouse is taken by a bearing that fits around the motor, as the tiny gearbox would not take the weight. The wheels are 3D printed and probably the only part that would be difficult to fabricate in any other way. We use a DRV 8835 dual motor driver, as although the wheels move in the same direction, when the servos move the wheels 90 degrees to turn a corner, two of the wheels then need to turn in the opposite direction. Thought has to be given to the type of wire used to connect the wheels, as they are constantly moving. We use multi-strand silicon wire. To measure the distance the mouse has traveled, we have a Hall effect sensor on one of the wheels, counting 1 millimeter magnets that are spread equally around the wheel. This gives a resolution of about 3.25 millimeters. We then increase the resolution by taking a percentage of the time measured between counts from the last count, and dividing that up so that you can add a bit more accuracy to where the mouse stops. The mouse uses 4 Emax 09 MD servos to turn the wheels and steer. These servos have 2 ball bearings on the output shaft. That stops the wheels wobbling, as this was a problem with the original ultra cheap servos we used. It's powered by 2 LiPo cells connected in series. With the servos, the drive motors, and the head motor, this means the mouse has 9 motors and gearboxes. So much for keeping it simple. The mouse uses VL6160X time-of-flight sensors that use a laser to send out light and measure the time of the return to give a distance in millimeters. We use 4 sensors mounted in the center between the wheels. They are I2C devices, but unfortunately the designers did not allow any way to permanently change the I2C address. This means to use multiple sensors, you have to individually start each sensor and change its address rather than this rather negates, I think, the point of I2C not requiring chip select lines. Duncan did a talk a while back on ways to get around this. We used a 1 to 8 I2C multiplexer. Has one input and up to eight line outputs. This allows you to address all the sensors individually. This is housed in the top of the sensor turret, so the whole thing only requires 4 connections to go up to the main board on the top. The sensors can see about 20 centimeters, so they can register walls along the next line and add them to the maze. As well as rotating the wheels by 90 degrees to go off in a different direction, the 4 servos allow for correction of errors whilst travelling forward. We have individual control of all the wheels, so we can move to the left or to the right without rotating the mouse. In an ideal world, this is all that would be required for this type of mouse. But of course, we don't live in an ideal world, and eventually rotational errors creep in and cause it to crash. Unfortunately, it's difficult with the sensor configuration we have to detect such errors. The solution was to add a small amount of rotation to the front wheels so they move a bit more than the rear ones. This causes a small rotation when moving away from the wall and will hopefully keep the mouse pointing in the right direction. All the software is written in the Arduino IDE using C++. And existing libraries where possible. This is the first mouse we've used C++ for. We have tried to make the software as simple as possible. The listing on the screen that you may or may not be able to read is the main loop for the mouse. Half the code is debugging code, but basically it asks the maze object which way to go, tells the mouse object to go forward until it finds a gap in the wall on either side or a wall at the front. It then reads the sensors and adds them and adds the current walls to the maze object. Then asks the maze object to solve the maze and checks to see whether it's in the middle. And then round it goes again. And it just continually does that until it gets to the middle. The mouse has no defined forward direction. You can put it at the start facing in any of the 4 directions and it will go off in the right way. The maze solver is the simplest possible that we could use. In fact, the code of the main maze solver is about 24 lines long. Not most efficient in terms of time, but it works and it's very simple to understand. It's the maze solver used by Alan Dibley's Theseus mice from the 1980s. We also added a connector for an open log serial logger that monitors the serial line and writes them to yet another micro SD card. for later analysis, allowing debugging while the mouse is running in the maze. Okay, so how do we get from recreating a 1980s Micromouse to the Terminator? Well, this is what you get when you hand over artistic direction to Jim while in lockdown. The rotating head is connected to the programming port on the Nano and is not required for the running of the mouse. It uses a Hall effect sensor and 4 magnets to detect when it's facing the correct direction. When first powered up, it does not know the direction the head is facing, so it will spin the head and time when the magnets are detected. As the magnets placing is not accurate, they were hand drilled, the holes for the magnets were hand drilled on the bottom of the head. The direction of the head can be calculated by differences in the timing between the readings. This mouse should be easy to customize. All you need to do is change the head and change the sounds on the SD card. So we have there a picture of Thumper, which can talk, an R2-D2, and the Terminator version. The sound system also turns out to be extremely useful for debugging. You can easily trigger off various sounds or phrases explaining what's going on, such as showing that it knows it's gone in a dead end or it's got to the middle, and also can be used for diagnostics. This mouse will tell you if the sensors aren't responding when it starts up, and other things. That's the schematic, and here's a video. You can see the head reset there at the beginning.
Judgment Day is inevitable. My CPU is intact, but I cannot control the hasta la vista, baby. This is the vehicle's house. Follow now! Trust me. I'll be back.
Okay, that's about it, I think.
Thank you, Derek.
Okay,
That's brilliant as ever. That's brilliant. So, has anyone got any questions for Derek?
Please, could we go back and look at the schematic?
Yeah, I was supposed to pause on that, but didn't. Where have we gone? It's back here somewhere. This whole thing is a video.
Thank you.
Yeah, as you can see, basically it's just a set of modules connected together with an awful lot of connectors.
So the sound player,
Yeah.
that's controlled with serial data?
Yes, that's connected to the serial port on the Arduino.
All right. So you give it an address and it plays you that clip or something?
Yes, absolutely, yeah. You tell it to play clip number 10 or clip number 3 or whatever it is, and it just plays the well, in fact it plays the third track on the SD card.
I find it just phenomenally brilliant.
Mm.
I think it's wonderful.
Thank
We
you.
like it. We like it, Derek.
Yeah. Okay. Well, we look forward to actually having a competition that we can run it at, and who knows what it'll turn up as.
We just need some competition, really, Derek. That's what.
Yeah. I think Duncan, you've built a half-size mouse, haven't you? How's that going?
I have here this wonderful C15 thing, which has got a 3.3 ampere hour LiPo that lasts about 2 minutes.
Oh, right. Well, that's all it needs if it's that fast.
It's not that fast. The problem really is debugging it when you've only got a 2-minute runtime. You know, you haven't got time to know what's going on.
Right.
I have started making a different version with different batteries on, but other things got in the way.
Yeah.
But I definitely think half size is the way to go. You can get everything done on a small table. You know.
Yeah. We had to build a maze. The maze is magnetic, so it sticks to nails that are in the main board. It's a wooden board, but we just hammered nails where all the posts go and the walls.
That takes up all the tolerance issues, doesn't it? Because you can jiggle it a bit.
You can. Yeah. I mean, the maze is not great, but it really, that's deliberately so. You know, if it'll run on a crappy maze, it'll run on any maze.
Yeah. Okay. Anybody else? Any questions for Derek?
Where did the motors come from?
The motors, yeah, eBay. They're used, I believe, in electronic door locks to open and close. So that they're little tiny motors that have a planetary gearbox, and you get them in all sorts of different gear ratios.
Are they N20 sized motors, or are they smaller?
Oh no, they're smaller than that.
Much smaller, yeah.
I've got one. You have one. I haven't got one knocking about. They've all disappeared.
I fear,
yes, they are
I
smaller.
fear quite often that it's a bit like talking to David Hannaford, who finds things at charity shops and places which you go, oh, I want one of those. But of course, there was only 3 in the whole world, and he's got them.
Look on eBay for motors with small planetary gearboxes, and you'll come up with those.
Was that running at full tilt in the video?
Pretty much. They're 3-volt motors, so we could turn them up to about 7 volts. That's probably about half. But
What sort of
there might be a lot of smoke.
What sort of gear ratio are you running at?
Oh, I think those are something close to 100 to 1. They're very, very high.
Yeah.
It's difficult to get ones with very low gear ratios. They have, in fact, if you take them apart, and you've got very good eyes because they are absolutely tiny. I've never seen a pinion gear on the end of a motor so small. They have 3 stages. So if you were really careful, you could probably take one of those stages out or fill it with super glue and make it up and reduce the gear ratio a bit. But yeah, they're difficult. We have found some that are about 20 to 1 gear ratio, but they're smaller than that. So they might be quite good for...
You run the risk of running out of torque then. That's the thing, isn't it?
Yeah, absolutely, yeah. So you'd have to make a very light mouse, which this isn't.
What does it
No
weigh?
turn motor head.
Do you know what it weighs?
What it weighs? I can tell you what it weighs. I have my scales, which have also vanished off the face of the earth. Oh, that's ridiculous. Where have they gone? They're always here. Can't see them. No. It's not a lot. It's a good about 200 grams, I think. You know, for a half-size mouse, it's huge. It's probably in scale with Thumper, which weighs in the kilograms.
So you have diagonal motors wired in parallel. Is that right?
Yes.
The diagonal pairs?
That's right, yes.
So it couldn't actually spin on the spot then? Because if you turn the wheels at 45 degrees, they'd be opposing each other, right?
It can if you turn the wheels the opposite way. Yeah, so because we turn the wheels and keep the wheel on the
they're
outside.
individually controlled, right? Okay.
Yeah, they're individually controlled. So if you turn the wheels in the right way, it could rotate on the spot. But it doesn't need to, so it doesn't.
Yeah. Brilliant as ever. Great to see. Okay. Derek, thanks so much.
One more thing. How much of the Nano have you used up software-wise?
The Nano, I have the thing here, so I can.
Is it vested interest in this one?
Yeah, the maze solver the maze solver directly, as it stands, can only do about 25 by 25 maze. So it leaves you to 16. I believe the one we've got is about 19 by 19. So it'll do that. But
20 by 20, but yeah.
20 or 20.
Yeah.
It'll do about 25. You run out of memory if you put it up to 32. But I think there are ways to do that. So it says it's used 54% of the program space, and with the 9 by 9 maze that's currently in it, 49% of the RAM in the Nano. So yeah, to go on a 32 by 32 maze, you'd have to be a bit creative, but I think the thing is so slow, I wouldn't like to run it in a 32 by 32 maze.
Even the contest ones in Japan, they're just tedious to watch in a full-size maze, to be honest.
Exactly.
Right?
I think it would be I think it would be a mistake to run a competition with a really big maze, or at least one that, because quite often you see very large portions of the maze that you just can't get to.
Well, they get 7 minutes to explore in Japan, and it's not uncommon for them to, because the runtime's only 12 or 15 seconds at the most, probably less than that. It's not unusual to find them taking 6.5 minutes. And with the best will in the world, you wish you'd taken a book.
Yeah. Okay. So, but running half-size competitions on a 16 by 16 maze, I think, is a fairly good idea.
Well, I've only got as far as half building a full-size one, so I shall have to work it the other way around now.
Brilliant. Okay, well, Derek, thanks so much